right? You've division by 0 if y is equal to 0. So the Pfaffian form I really love because it's much more sort of level-handed. It doesn't distinguish between x and y. See, this differential equation is just as well defined for x being 0 as it is for being y being 0. And it will, what I have boxed in green will agree with the black equation wherever it's defined. And it also extends past where it's not defined. So this is one of the reasons the Pfaffian form is like logically nice. It's more general in its applicability for a given example. All right. Enough terminology. Can you guys tell me, this is df, this is the differential of what function? We told you how to take the differential of functions, total differential in calculus 3. Now I'm simply asking you to undo it. What? 1/2 x squared, yeah? Plus what? 1/2 y squared, right? So this differential equation in green can also be written as a differential equation, pun intended. I mean, this is the same as the differential of this function is equal to 0. Once you do that, what's the solution? The solution is level curves of that function. This is the method. Of course, I prefer to write the general solutions here like x squared plus y squared equals to r squared, right? And so you can see what we're dealing with. And you can understand why it is that y equals to 0 gave us trouble, because that's the place where we have vertical tangents in the circle, which is precisely the place where function theory breaks down, in the sense that y is not a function of x at those vertical tangents, right? And yet it's still a geometrically reasonable thing as captured by the Pfaffian form of the differential equation. So what's the method? That's what you're asking, right? What's the method? The method of exact equations is given a differential equation, you put it in Pfaffian form, can you recognize the differential equation? Can you recognize m dx plus n dy as being the total differential of a function? And then the natural question to ask then is, well, is this always successful? Is it sometimes successful? When is it going to be successful, right? So the question is, given m dx plus n dy, equals to 0, when can we see m dx plus n dy equals to df for some f? To put it in better mathematical terminology, when does there exist a function f which attains m dx plus n dy as its total differential? All right? I mean, it was true here, but it's not going to be generally true. There's lots of differential equations which are not exact, okay? That's where Green's theorem helps us out. Okay? Yeah. Oh, you just, it's cool. Still 20 minutes, good. Let's see here. So, you guys are bored with the joke already. All right, it's good. It's good, it's good. So consider Green's theorem. All right? If we have the integral of m dx plus n dy, what should this be? What is this? If we're looking at a solution to the differential equation, m dx plus n dy is what? It's 0, right? So this is equal to 0, assuming have a solution. 2 star. Let me give this equation, the differential equation, a name. I'll call it star. Right? That has to be 0. But what else? And I can do that for what? For any boundary to some region in whatever domain we're looking at. But Green's theorem says what? What does Green's theorem say? It says that this is equal to the integral of partial n, partial x, right, minus partial m, partial y, dA. But the thing is, I'm still not, how to say this. See, I'm not entirely convinced by my argument now. Curses. Sometimes you try out something new and I'm not entirely convinced by it. Oh well. I wanted to say, okay, so that's equals to 0, so that forces partial n, partial x to be equal to partial m, partial y. But I'm not entirely convinced by that because, I mean, I don't know, are you guys convinced? What's that? Shrink the region down to a point. See, but I'm also assuming that the solution parameterizes like a simple closed region. I don't know if that's reasonable. I thought I had something here, but I guess I'll have to fall back on my usual argument. Stink. All right. I mean, this is not bad. It's just I can't logically get where I want it to go. I'm sorry, guys. You try some things. Sometimes they don't go well. It's not wrong. It's just not what I need to get to. So here's the thing. More to the point, if m dx plus n dy, I'll fix it right here, is equal to df, what's that mean? df is what? df is partial f partial x dx plus partial f partial y dy, right? So you can read off that this must be that, and that must be that. In other words, m is partial f partial x, and n is partial f partial y. What do you know about partial derivatives? Let's assume that m and n are continuous, okay? Which means this f, if it exists, is continuously differentiable. Whatever that means. Remember what we could do? What's the difference? If you differentiate y first and then x, or if you differentiate x first then y, does it change the outcome in Calc 3? Remember we say partial differentiation commutes. Remember that? So if I calculate partial squared f partial x partial y, that should be partial squared f partial y partial x, right? In other words, partial x of n should be equal to partial y of m. Oh, I see what I should have. Now I realize the error of my ways. I was putting the cart before the horse, so to speak. I should argue what I just argued in red to start with. So suppose it's an exact equation. That means that m is partial f partial x, and n is partial f partial y, right? Then, so I must have this relation between the partial derivative of n and m with respect to x and y respective. Once you have that, you can verify that this in fact does give you a solution with Green's theorem, right? Because once I know that partial f partial x, partial n partial x is equal to partial n partial y, what does that do to this? That makes this 0, right? And it makes it 0 for what? For any region in which this holds. And so the boundary There's still something I don't understand about that. I have to stop. I have to stop. But let not my confusion be yours. This is the theorem. The theorem simply says this, that partial n partial x has to equal partial m partial y for an exact equation. And if I was thinking more clearly today, I could explain to you carefully so if it's exact, that has to happen. All right? The converse direction, if that holds, then it's exact. That's only true if that equation is realized over a simply connected region. It's possible to have partial n partial x equal to partial m partial y over a region with a hole in it, and yet still not have a function for which it appears as the total differential. It's the same issue we raised in Calculus 3 with the conservative vector fields on simply connected domains. It's the same math. You can only, like, given this, the existence of f is only true if that equation holds on a region without holes in the plane. But that's subtle. I can show you an example of it failing if you'd like. Yep. Oh, no. The standard example of it failing would be this: minus x dy plus y dx over x squared plus y squared equals to 0. Here you have m is y over x squared plus y squared, and n is equal to minus x over x squared plus y squared. You can prove that partial m partial y is equal to partial n partial x, but this is not equal to the differential of a single function. The reason for this is that this is defined on the punctured plane, right? This is everywhere except for 0. And what you're looking at is actually the total differential of the angle function. So you can't define an angle that's differentiable all the way around. Somewhere the angle has to have a discontinuity, and where it has that discontinuity, it also has a fall from differentiability. And so but this region is not simply connected because it's missing a hole, right? If you want me to find a solution to this differential equation on like a half plane, I can do it because that's simply connected. So this is a subtlety that almost never comes up in problems, so I'm not sure why I'm telling you about it at the moment, but anyway, I guess just to scare you. Did it work? The natural antidote to being scared, though, is just go do some problems, right? I have oodles and oodles of examples posted on the website. You're not alone. Come to me for help if you need it, right? But first, work first. And you can ask questions next time if you got them. Thanks, guys. Again, thank you to Kang for reminding me I had class at this time today. My office hours will be revised, obviously.